So this is basically a press release, I guess. I've got these two tools I wrote that are kind of cool. Um, they're both very interactive and fun to use, and they can be educational and helpful. This one mostly is helpful if you're designing a bath, and this one's mostly helpful if you're going to be, well, for a few things, if you're going to be testing a big mirror like a 24-inch 3.1, or um, to help you understand things about the bath. Does interferogram simulations. I'm going to talk about both these tools. They're both open source. By the way, this video is not going to be as well polished as my more recent videos. This is just kind of a quick one. They're both open source, Creative Commons license attribution, so you can use these commercially. You can copy them. You can even sell this software if you want without paying me a thing. But there are some restrictions. You can just read the license if you click on that. I'm going to talk about this one on the right first. I call it the diagrammer. This is where they're located. If you can't read what I'm highlighting, you can just go to the links in the description. If you just type Control U on one of these, which is View Source, here's all the source code. It's all contained in a single file. So if you want to look at the source code, edit it, change it, write your own, publish it, you're on your own, whatever. It's all fine as long as you follow the rules in here. You have to attribute me. I'll talk about this tool first, and this one second. So this one I call the diagrammer. I released this one a few months ago. So let's just go over it, I guess. So basically the laser beam, this is a bath interferometer. So one of the things you can use this tool for is for designing bath interferometers. Like you might want to know if this flat mirror here is big enough. Because mine is, I think I've sold ones with 10 millimeter flats here. And I want to know if that was big enough. So that's this number here. And the answer is yes, it's plenty big. So these gray things you can grab and move. But most of those things you can also change up here, but there's more options up here. So you can set the F ratio of the mirror. You can see this returning beam will change size. So when I change this from a 3 to say a 9, the only thing that really changed was this. Actually, let me change it back to a 3. So if I change between 3 and 9, the only thing that changes is the size of this, the cone, the angle of this return beam. So this, let's start at the beginning. The laser beam comes down here. It's the purple. The blue passes through the splitter. The red bounces off the splitter. The red is the test beam, which is testing the mirror. Testing the mirror goes through this diverging lens, comes to a focal point, and then spreads out. And that's a cone of light that covers the mirror to be tested. In this case, an F9 mirror. And then the light comes back, a lot smaller beam, because it's only the light from the mirror comes back, and the mirror is smaller than the test cone, hopefully. You need a bigger test cone than the mirror. It comes back here, bounces off the flat, bounces off the back of the splitter, and then comes out over here where it's imaged, either in your eye, in your camera, on a piece of paper, whatever. And then it also passes through the splitter, the blue lines, and that's your reference beam. By the way, this is a very fat laser beam. I'm going to make it a little more realistic for my fatter laser. And in fact, if you have a typical laser, it's probably more like 3 millimeters. But let's put 4 because that's the laser I sell the most. This, if you read this text, include the full beam, not just the usable beam. So, because you want to make sure that, basically this is to help design and stuff and testing stuff. You want to make sure things don't happen. If you look down this corner here, if I go too close, and here it clips right there. So when something's wrong down here, you get a red text message, and then usually you get like a purple dot kind of showing you where the problem is. So I just explain it in words and pictures, basically. Where was I? So the laser beam comes down through here, goes off the flat. This is the reference beam, touches the mirror in a tiny spot, comes back from the mirror, goes through the divergent, and then finally converges and then diverges out. Also, I include the index of refraction of the splitter itself. So if I set this to 1, which is like air, it's like goes right through it. It's not realistic, but it's close enough. If I set it to 2, that's actually better because the beams are more contained in here. But usually they're around 1.5, 1.6. So you can probably just leave that as it is. So this 9 here affects the size of this returning beam from the mirror. You can see it's pretty small. So your camera only has to catch that little. So testing f9 mirror is a lot easier than testing, say, an f2 mirror where you get a much fatter beam coming out of here, and you need the camera a lot closer to the splitter to get that not clipped, not vignetted by the camera lens or by parts of the camera. Focal length of diverger. That's this thing is the diverger. So it's set for 7 millimeters. Yours might be 15 millimeters. And it changes everything. You can see these beams come together more here, whereas before it was further out. And then you can change the position of this. In general, you want your diverger as close to the cube as possible where it doesn't bump into it. You want to be able to rotate the cube a little bit. So you don't want it like touching. You don't want to glue it on either because you want a biconvex diverger. I talk about that elsewhere. Anyway, here's the size of the splitter, 15 millimeters. That's a good size, but you can investigate, would you be able to build one out of a 7 millimeter splitter? So you can type in 7 here, and then you can see where the positions of things are, and you'll see that it's getting more and more difficult to accommodate the laser. So there's a splitter rotation. You can do it down here with the handle, or you can type in a number here. You do want to rotate a little bit to get, well, if you don't know why, then don't worry about it. You'll learn someday. Laser beam offset from splitter center. That's this position here. So if this is 0, it should be right in the center. Laser beam width. I already played with that. Splitter index of refraction. I already played with that. Beam shear. That's the last thing you can play with. Now, some of these things you can play like this. You can move up, down, left, right manually. It's not really controlled up here. That's probably the only one. All the other ones, when you move these, it changes things up here. So beam shear. So when you add some tilt, when you move the bath, let's make this like let's start over. Hit refresh. This is how when you come into the page, it's like this. So this is already at plus 50. That's how I default it. So let's show you what that looks like. If I set this to 1 versus 0, you can see what's changing here. So what's happening is if you move the bath by 1 millimeter to the side, well, you have to move it a half a millimeter to get a 1 millimeter beam shear, I guess. So if you move it a half a millimeter to the side, the returning beam will be like this. This is, a little exaggerated, probably more accurate like that. Anyway, the point is this blue area, this reference beam, gets shifted. And you can see that when you're adjusting the bath, when you're adjusting the tilt, you can see how there's the I-gram, and then there's this, darker area around it. And when you slide it like this, 50 fringes, I can use this tool now. 50 fringes is about like that. I like to do at least. Dale recommends 40 fringes, I believe. I like to do 50 to 100, 40 to 100 fringes. Anyway, to get 50 fringes, for this particular mirror, an f3 mirror, you only have to move the whole bath by 0.1 millimeters. Or half that, really. That's the shear. I believe it's half that. But if you had an f10 mirror, and you hit this, you have to move it quite a bit more. You have to move the bath by half of 0.3 millimeters. And this is what it would look like. You kind of get an idea, and you can see if it's going to hit the edge of the cube. So when you combine too many of these things, you can get these errors where the reference beam can clip. So the main purpose of this tool is just to kind of, if you're designing a bath, to get an idea of how much to the side the laser can go, where can you place the flat, where do you want to place the diverger, how big of a splitter can you use, how big of a laser beam can you get away with, or should you stop it down with some kind of aperture, and so on. And you can see what that would look like with your particular mirror under test. The lower the number here, the lower the F number, the more difficult it'll be. But with this setup, most of the setups you'll see here are pretty easy. All right, the last thing is to explain about these three dots, which will take, well, these two dots, the green and yellow dot, which is the most complicated part, I guess, is described right here. And the quick answer is the green dot is where you want to focus things when you're setting up the bath, and the yellow dot is the center of curvature of the mirror that you're testing. So if you're testing and you're at a focus of 0, if you're right at conjugate, I think is the right word, then the yellow dot, the center of curvature of the mirror will be here for this particular exact setup, and the green dot, where it's focusing the return test beam, would be right here virtually. I mean, if it didn't bounce off this mirror, that's where it would converge. And so when you're setting up your mirror, setting up the bath, let's say you had a F4 mirror, that doesn't really affect things. What affects things more is the distance between the two beams. So if you move the laser over here, the beams are closer together, and so the green dot's now lined up with the center of the cube. If the laser's here, the beams are further apart, the green dot's moved to the left some. Also, the position of the diverger matters, affects the green dot. So if your diverger's close to the cube like this, and your beams are at a reasonable distance, for me, often the green dot is at the back of the cube. So I usually, when I'm setting up my bath, I relocate the bath. I locate the bath low so that the two returning beams are high, going over the bath, over this mirror. And I move a piece of paper back and forth in this red beam to find the focus point right here. And I want that focus point to be lined up with the back of the cube for my interferometer, which, every interferometer is different, but, for the most part, if you're using a bath that I sold you, then this is probably about your beam separation, and this is about your position of the diverger. The yellow dot, again, is the center of curvature of the mirror. It's halfway between this point here and the green dot. And this green dot is positioned in 3D space, but I can only show it in 2D. But you might only care about it in 1D, which is like that it's at the back of the cube. This yellow dot is halfway between the green dot and this point. So it's the focal point of this beam, that's the test beam here, and the test beam when it comes back. It's halfway between. So if you want to measure the center of the radius of curvature of your mirror using a bath, which is, better to use a Foucault. If this is a Foucault test, you'd put the razor blade right here. It'd be right at the center of curvature of your mirror. The distance from here to your mirror is exactly double your focal length. So if you're trying to figure out your focal length, because you want an accurate focal length when you're using DFT fringe software, you could measure to this point from your mirror. But to measure from this point, you need to know what your beam separation is and so on. This shows how you calculate where the yellow dot is. So you could use this formula. All you have to know is, let's read it. It's the beam separation distance divided by 2 behind the diverger. So if this is 10 millimeters, it's 5 millimeters behind the diverger. So right there. So you can measure with a tape measure or something from here to the mirror to get a pretty accurate distance, which you need if you're going to be using this to test a mirror. So that's it, I think, for this tool. Let's talk about this cool toy tool. So this is an interferogram simulator. There's one built into DFT Fringe that has more features than this for the most part. I only let you change 4 Zernike terms: spherical aberration, tilt, focus, defocus, and astig. And in DFT Fringe, you can control, I think, 42 or so of these. You have to type them in, and it takes a second or two to get a result. But this tool is so fast. In fact, here this tells you how long it took to do a frame. So as I move it, you can see this number jumps around. It can do about 20 a second or 30 a second. Well, about 20 a second frames, which is really nice. Looks like a smooth motion. So so let's start at the beginning. Let's refresh this to see when you first come to the page, it defaults to the smaller size. You can put the f ratio of your mirror in here, and the diameter in inches. This is a really big 24-inch f3 mirror that it defaults to. You could put in your kind of constant. These are the same parameters you'd put in DFT Fringe in your laser wavelength. By the way, if you put in a wavelength like 555, if you're using a 55 nanometer green laser, I don't think that's actually a thing. I also changed the color to match. So it's kind of cool. I don't know. This color's all in between. So these are the same 4 parameters you put in DFT fringe to figure out the null, and that's what I'm doing here. I'm figuring out the null. This is the exact same null you would see in DFT fringe. It's also the spherical aberration of the wavefront coming back. It's how high this ridge is here, basically, is one way to look at it. In waves versus the valley here, sort of. So this is high point, there's a low point on the mirror, that's a low point. And this ring here is a high zone. And that's what you want to get a perfect parabolic mirror. Anyway, the size of this hump here is related to this number in waves. This is the same as the null value in DFT fringe. If you don't understand what the null value in DFT fringe is and how it's calculated and what the point is about it, watch this video on my channel, Zarnicki Terms. This is much better video than the one you're watching now. It's better produced, and I explain, I hope, really well what this whole null thing's about and what spherical aberration is when you're talking about DFT fringe and I-grams. X tilt is a lot easier to understand. That's when you're moving the bath in this image up and down, because it's an overhead view. I assume. I guess some people's bath may be turned 90 degrees, but whatever. So that's the tilt, and I only do positive X tilt. Well, you can type a negative number here. Type whatever you want in here. The slider only does positive, because that's really all you need for the simulator, because it's symmetrical, because I don't have anything that's non-symmetrical in X here. Although I suppose it'd be nice to have Y tilt. I don't know. All right, so these 4 numbers create the Z8 term. You can play with the Z8 term, and when it does, you can click here to get back to the computed value based on those 4 numbers. Let me show you something I discovered that's bizarre. I'm going to set the tilt to around, if you set the tilt to around 20, and you set the other 3 things to low values, and then you play with these. So I'm going to show you the A-stig. So this A-stig, the higher this number is, the closer the top and bottom of the mirror are, and the further away the sides are. It's kind of a potato chip, like a Pringles shape, where these are like flapping up and this is like flapping down. And when I move this side to side, you can kind of see that here it looks higher, and here it looks higher, and the middle looks lower, and the sides look lower. I think that's so cool. So it's kind of almost looks 3D. It's just a strange artifact. It's not really a 3D representation. It's just a weird artifact. And it works if you have X around 10 or 20. Let me put up to 20 here, or 15. It works pretty well around it works best when you have about 20 fringes, I found. And then the defocus. So if I move it in this range here, you can see that it looks like a bump, a big bump in the middle here, moving right, left, right, left. And that's actually opposite of how this defocus is. When this is positive, the top is actually low and the edges are high. So obviously it's a bad 3D representation, but it's not even meant to be a 3D representation. It just kind of looks that way. And then finally, the spherical aberration. Yeah, in this range here, do you see? It looks like there's a bump here also, but a smaller bump. It looks like it's high in the middle and high in the edges, which is really cool, which is kind of what spherical aberration is, but it's upside down. When you have negative spherical aberration, the center is low, the edge is low, and then you have a high ridge in between. Anyway, I just had to show that because it's kind of cool. Let me just do this one more time. You can do it yourself. Just set the tilt to around 20 waves and set the other 3 to close to 0, and then you can play with each one, and you'll find there's a part where it looks 3D, and then there's a part where it doesn't look so 3D. Okay, let's start up from scratch. So what's the whole point of this? Other than, oh yeah, that's what my... so there's a couple points. I guess I'll get to the main reason I created it in a second, but so there's 2 reasons that I find this tool useful. One is you can look at what your mirror looks like. Let's set the spherical aberration to like a mirror I've tested recently. And this looks a lot... I mean, I recognize this. I've seen this so many times. Maybe 100 times I've seen this. And this is what it looks like when I'm trying to find get down to defocus at close to 0 under a wave. So now I realize that even if I want defocus of one wave, I don't really have to get. I usually try to see there's 1, 2, 3 black rings or 1, 2, 3, 4 red rings. I usually try to get that down to like 1. I never quite get there, and I realize if I want one wave of defocus, 4 rings is fine. Anyway, if you want to do negative defocus, you have to type it. It doesn't really look a lot different. It's different. And then there's, what was I going to show you? So that's one use of this tool, is kind of to recognize what these look like, what tilt looks like. Well, tilt is the more tilt you have, and you get tilt by moving the bath to the side, the more lines you get. And when the Zernike term is at 23 waves, you actually get double that, 46 lines across here in general, assuming you don't have a lot of these other terms. So that's one use for this tool. The other use, which I think is the main reason I created this tool, let's start back at the beginning, is has to do with this line down here. So if I'm testing a really difficult mirror, like a 24-inch f3.1, you get a lot of spherical aberration here. That's why you can see this ridge going all around here. I'm going to make this bigger. I'm going to go to 1,000 pixels. So there's that ridge going around there. Let's just scroll down a little bit. So I think because it's got two bullseye patterns, DFT fringe will probably have a hard time with it. This is like a low point in the mirror. It's lower than the surrounding area. I guess it's not as low as over here. And this is a high point in the mirror. And so DFT fringe and your eye can't really tell which one's which is the high and which is the low. Or will DFT fringe get confused and think they're both high points, or will it think they're both low? I don't know. DFT fringe might be able to analyze this as is, but I suspect it could have trouble. So one way to get rid of one of these, or in both really, is to add a lot of tilt, and that's what we usually do. The problem is, to get rid of both of these, you have to add a lot of tilt on a mirror with a null of -10. That is it. You have to add a lot of tilt, and you can see I had to go up to 126 waves of tilt. And look, it's complaining in red here about something. I can say show location. So what this is saying is that this area of the I-gram, the fringes are so close together that if it's 1,000 pixels from one side to the other side of the mirror, and you can probably get a lot more than that, you can probably get up to 2,000, but there's 2 pixels per fringe. Now Dale says you need 3 pixels per fringe for DFT fringe to analyze the I-gram. I've gotten it to work pretty well at 2.5, and at 2.8 I think it's fine. So I'm not sure how he got 3 pixels per fringe, because I found that 2.8 seems to be enough. I've gotten I-grams that look a lot like this one to work just fine in DFT fringe. I-grams, I did a test where I had 360 fringes going across, and it worked fine. But anyway, you want about 3 pixels per fringe minimum. So what can we do? Well, look, there's a hint here. Add some defocus. So if you start adding defocus, and positive defocus means you're moving farther from the mirror. So basically, you're moving the bath away from the mirror. If you do quite a few waves of this, suddenly this point jumped over here. Look, we got up to 2.2. Now, actually, I think we can reduce the tilt. I forget. So that moment it jumps, this circle jumps, is also where this number is the highest. And look, we can get it almost up to 3. That's close enough to 3 that it would work. Now you can just go to 2,000 pixels, and now it's saying it's double that. Wait, why did it... Wait, it should have gone... 2.95 times 2 is about 6, right? Oh, yeah. Okay. Let's maximize this. Yeah. Man, it's hard to show this. Oh, I can shrink the screen a little bit. Yeah, okay. But if we lower the defocus, it starts turning red even though we're not down to below 3 pixels, because the lowest, if you have an I-gram where it's 2,000 pixels across the mirror, the lowest I've ever done is 5.6 pixels per fringe on a 2,000 pixel image. And that's the one I referred to that was 360 fringes all the way across. So if you do 2,000 divided by 360, I think you get 5.6. So this is kind of a warning. That's why it turns red. That hey, you may have trouble. This is a pretty amazing igram, pretty difficult igram to achieve. Now I've achieved it. I think I could probably do better, but you might want to just add some more defocus here. Let me go back to 1000 pixels. Let's go back to normal resolution. So anyway, that's pretty much it about this tool. I showed you that you can change this to get a higher resolution image. It does slow down. So when I'm doing it here, you can see that it takes, you can only do about 10 frames a second. And when you're down here, you can do a lot more frames per second, like 100 frames per second. So I think that's it. I sell bath interferometers. If you go to gr5.org/bath, I have lots of advice if you're making your own interferometer, or you can just buy one from me. You just click on this link. It takes you to my newer store. I just put up a newer store recently. This is in 2022, and I guess it's slow. And I have this cool thing to help you select parts here. So if let's say you're testing like an f4 mirror and an f5 mirror, and that's kind of the range of what you're going to be testing. Now you have kind of two options. You can choose the cheaper laser or the laser that's $14 more. I recommend the glass laser. It's just a better laser. It's easier to clean and stuff. But anyway, the other thing is with this combination, I recommend you get two different divergers, which is going to cost you an extra $10. So really, this is only $4 more in this one specific example. But let's say you choose this laser, and then you could have added a lot more mirrors. And then you can go in through here, and you can see the price is $209. You can save $50 if you do this. You're down to $159. And then you can hit add to cart and so on if you want, or you can email me with questions. I do ship internationally. It may have an issue with that if your country isn't in my list yet, but just email me if it comes up that way. It'll tell you to email me. So that's it. I hope you like this video.